Welcome to the fourth lecture video in our Class 12 time series of lecture videos. We ended the third one looking at cumulines, and basically we decided, you can have chiral molecules without having a stereocenter. And here is another example of an instance where you can have chiral molecules without having a single stereocenter present. This typically involves hindered rotation. In our prior example at the end of our third video for the Class 12 set of lecture videos, we used double bonds. In this case, we're using four-membered rings. So this particular molecule with a spirocenter is achiral. It has two planes of symmetry. That's our spiro 3,3 heptane molecule. You exchange one of these and two hydrogens for a methyl group. You're still achiral, you still have one plane of symmetry in this molecule, but then you exchange one of the two hydrogens at this carbon for a methyl group, and lo and behold, you have something that's chiral. Similarly, sometimes you can get things that are hindered in terms of their ability to rotate even around carbon-carbon single bonds. Here we have a biphenyl structure, so a couple of benzene rings. We'll talk a lot about benzene rings in the second semester. One could imagine that if X and R, these groups that are substituting hydrogen, presumably, when they get big enough, that free rotation ceases around that carbon-carbon single bond. So you might be stuck on one side or the other, and those would be non-superimposable mirror images. And sometimes you can even racemize these depending on how much you heat the molecule. These are typically things that are employed in chiral catalysts as ligands, and they impose a chiral environment around the catalytic center and allow it to give you stereospecific outcomes. So now that we have all of these ideas about stereochemistry under our belts, we could revisit radical halogenation reactions. And now we can show all parts of certain halogenations, including stereocenters. So let's, for instance, take butane, the bromination of it. We know if we're doing radical bromination, we know our bromine is going to be more selective for secondary hydrogens than it is for the primary hydrogens. You might get trace amounts of 1-bromobutane. But if you're aiming at monobrominated products, you're going to get a lot more of either R or S, 2-bromobutane. So what stereocenter would this one be? Hydrogens pointing back, priority 1, 2, 3. This one's going clockwise, so clockwise is R. This one looks clockwise, but hydrogen's in the front, so it is S. So if you start with no optical activity, butane is not optically active, nor is bromine, you get no optical activity from a radical halogenation. So in other words, 1 and 2 are formed in equal amounts. So one could imagine the intermediate radical, where you've abstracted a secondary hydrogen. It is prochiral, but on its own it is achiral. So it could either react with diatomic bromine from the top lobe or from the bottom lobe. And there's nothing that would differentiate either of those reactions in terms of energetics. So the transition states would look like mirror images of each other. We call those enantiotopic transition states, and so they would have the same energies and they would occur with the same speed, so you end up with the same amount of either 1 or 2. I've just rotated these in certain directions so you can see, right? You could re-rotate one back to this bond line diagram if you're tricky. So with that, we have one more page for this particular video talk. Here we go. 1 and 2 should be of the same energy, and in fact the transition state's leading to 1. or 2 should be at the same energy because they are enantiomeric. Sorry, I got cut off there. Enantiomeric transition states for 1 and 2. They look like mirror images, so they have the same energy, so the rate of formation of 1 and 2 is the same. What if you start with something that is optically active? So let's say, for example, we're going to chlorinate R2 bromobutane. Somehow we isolated our R2 bromobutane. We're going to just proceed with chlorination. Well, chlorination is less selective. You might chlorinate some primary carbons, either this terminal carbon or the other terminal carbon, or you could chlorinate the secondary carbon that's left that is not necessarily the carbon that is the bromine, or you might attach to the bromine, or you might even chlorinate that. So 5 and 6 are just enantiomers, right? You would expect 5 and 6 to be produced in the same relative amounts. Not really much you could say about 1 and 2. They're constitutional isomers, not really stereoisomers. Because they are not molecules whose atoms have the same connectivity, are they? 3 and 4, however, are stereoisomers. You've got an RR and you have an SR. What kind of stereoisomers are 3 and 4? Well, like I said, the expectation for relative amounts of 5 and 6 should be formed as a 1-to-1 mixture because they're enantiomers, and the transition states would have the same energy. However, 3 and 4 are diastereomers, so they would have different energies. Here we're showing what? 5 and 6, right? We've abstracted the hydrogen on the carbon bonded to bromine, and this is an achiral intermediate, and our chlorine could come from the top or the bottom and give us 5 or 6. The topic of the next video will be, the diastereomers 3 and 4. So what can we say about them and what we expect for them? And so I will see you in the next video.